Hello everybody. In this video we're going to talk about finding confidence intervals with means and standard deviations. If you haven't already watched the video about finding confidence intervals with proportions, please watch that one first because that's where I really explain what a confidence interval is. Here we're just going to look at some calculations. So we'll start here with means. If I'm trying to estimate the population mean by taking a sample, again our point estimate, our best guess for what mu would be, our population mean, would be whatever the sample mean is. But of course, just like with proportions, we've got some amount of error here, so we want to know what kind of range we should have. The format here looks just like it did for proportions. We're going to take that point estimate of x bar and add or subtract the margin of error e. Now when we're computing e for a mean, there's actually two different methods of doing this. If we know sigma, right, this is the population standard deviation here, then we can use this formula that looks a lot like what we did with proportions. So this is our z alpha over 2, that was that critical number, times sigma over root n. So this uses a standard deviation, and I actually mentioned that we were using a standard deviation with proportions, although it didn't look the same since we were using sort of a binomial distribution. The problem is with this method is that typically we don't know the standard deviation of the whole population, because that's something that would be difficult to measure. You know, if we don't have data on the whole population, it would be unusual actually for us to have that information. But if sigma isn't known, that puts us over in this category. We can't use this same computation because we don't have the sigma value. So what we use instead is a different kind of critical number. This is a t alpha over 2. This is still a critical number, but it's using a different distribution. And then the rest of this would be s over root n. So they look pretty similar, but here we're using s, or the standard deviation of the sample, and that is typically something that we would be able to compute. So over on this left-hand side, we're using a z-score distribution, which is also just our normal distribution. But on this side, we're using a t-score, and this is called the student distribution. This sounds like kind of an odd name. Student was actually a pseudonym for the person that discovered or invented this distribution. So he published it under the name student. So depending upon what type we have, we'll use either this first formula here or this second formula here. And I'll look at how to find the t-score in just a minute. You can also do these on the calculator. For the sigma known version on the calculator, we're going to use a test called the z interval. And this is in the same place that the tests were for looking at proportions, that same list. For when sigma isn't known, we can also compute this on the calculator using a test called the t-interval. So again, this second one here is what we'll typically be using, but you may have some problems where you know the sigma value. Now notice that both of these have a second requirement, that our sample size is at least 30 or that our data is normally distributed. This has to be true, otherwise this isn't going to work in determining our error. So I have an example here. I'm going to give you an example where the sigma is not known, because if sigma is known, our calculation is going to be very, very similar to what we did with proportions. You'll find the critical number in the exact same way. So in this case, we've got 10 randomly selected men. They take a stress test, and then we look at their pulse rate. So their mean pulse was 126 beats per minute. Now this is the mean of the sample, so I would write x bar is 126 beats per minute. And the standard deviation of their pulses was 4 beats per minute. Again, this is for the sample, so this is s. Notice we don't know what the standard deviation of the whole population is. That's not information that we're given. So what we want to estimate is the population mean, right? What is the pulse rate for all men if they took this stress test? And we're going to use a confidence level of 95%. So just like before, we want to compute our margin of error. Now most of this information we already have. The little s would be 4. N is the number of people in the sample, which was 10 in this case. So the only thing we have to determine is this critical value. Now before we got our critical value using the z-score table, in this case what we're going to use is a different table for t-score values. The picture still looks the same. We're looking at sort of a bell curve shape. Our t-score is going to be this cutoff value, where in the middle we have 95%. That was our confidence level of 95%, which means that the tail ends that we're excluding, the total area in there would be 0.05, which means that this little tail is 0.025, this little tail is 0.025. Here's the t-score distribution from your book. Again, this is on that pull-out cardboard sheet. It's also in the appendix. So you'll notice that this table looks quite a bit different. What they do have is the area in the tails. Now, based upon our picture, the area in one tail would be 0.025, or the area in both tails is 0.05. We can use either of those to look that up here. So the area in two tails, 0.05, you'll notice that's the same column as area in one tail, 0.025. So we're going to want this middle column. And then we need to know what's called the degrees of freedom. And for the t-distribution that we're using, degrees of freedom is just n minus 1. So n minus 1 in this case would be 9. So we're going to look in our table under degrees of freedom 9, and we're looking at that middle column, so 2.262. So we have 2.262 times our standard deviation, which was 4, divided by the square root of n, or square root of 10. And then we can just enter this into a calculator, and this comes out to 2.8612 approximately. So we've computed our e value. Now we're going to write down the interval. So again, we're estimating the mean of the population. This is going to be the mean of our sample plus or minus the error term. And in this case, our mean was 126, and then our e value we just computed. So if you take 126 minus this value and 126 plus this value, we end up with an interval of 123.1388 and 128.86. Looks like I just rounded to 2 decimal places there. So this would be the range of heart rates that we would expect for the mean of essentially all men taking this stress test. Now again, just like with the proportions, we can also do this calculation on the calculator. So let me show you that. I mentioned a little earlier in the video that we're going to go to the same test menu. So this is the stat button in the middle of the calculator. Go over to tests, and in this case we're doing an interval, and there are 2 main options here. There's a z-interval and a t-interval. So this depends upon whether we're using the z-score or the t-score, depending upon whether we have our population standard deviation or not. So we use t-scores here. We're going to do a t-interval. And you have 2 different options. One thing you could do is actually put in data values. You could enter those into the lists and calculate it this way. But typically we're going to have the statistics already calculated. So we go through an input. First is the sample mean, so that was 126 here. And then this is the sample standard deviation. So this was 4. Then n, this was the number of people we studied, this was 10. And our confidence level was also 95 here. So here's the interval this comes up with, 123.14, 128.86. These are the same numbers that we got from the formula. So again, I want you to understand how to go through this formula, and in particular how to find the critical values here. That's sort of the tricky part. But in practice, most of the time when we find confidence intervals, we're just going to use the calculator because it's so much faster. So the next thing I want to look at is finding a confidence interval for standard deviation or for variation. It would be the same process for either. So just like with mean, the point estimate for finding the population standard deviation or the population variance is just the standard deviation or the variance for the sample, so no different there. Standard deviation is a little bit trickier because we're not using a z-distribution or a t-distribution. We're using what's called the chi-square distribution. Chi is a Greek letter. It looks kind of like an X with a big start, I guess. Or when I write these, I do kind of a big first line and then just cross it. So this is chi-square, and the tricky thing about the chi-square distribution, we can still look these numbers up in the table. We're going to look through the table at A4. But this distribution is not symmetric like our normal distribution is. It has kind of this long tail. So the idea is still the same, where the middle part would have, for example, 95% area or 0.95. So we're going to have to look up two different critical values. And if you look at the formula, you can find this in the book, and it's also on the pull-out sheet. There's great notes with all the formulas for this stuff on the pull-out, so that's a really good reference for this. Our standard deviation is in this interval. This is our interval estimate, but we have to compute both of these bounds separately. So you'll notice there's a chi-squared r and a chi-squared l. Those are the left and the right values coming from our chi-squared distribution. So let's look at an example so we can see how to get these values. So in a sample of 30 fun-sized packs of M&Ms, the mean number of M&Ms was 23.8, so that's the mean of the sample. That would be x bar, which I actually didn't write down here. So x bar is 23.8, so about 24 M&Ms per pack, with a standard deviation of 2.71. This is the standard deviation of the sample, right? Find a 90% confidence interval estimate for the standard deviation of M&Ms. So we're using 90% confidence, and we're trying to estimate the standard deviation of the whole population, right, or sort of any pack of M&Ms. Now the n value here was how many things was in our sample. There were 30 packs in the sample, so that would be n. And the degrees of freedom for the chi-square distribution, this is the same as for the t-distribution. This is going to be one less, so 29. So we need to look up both the left and the right chi-squared values. Let me show you the chi-squared distribution table. So here we go. You'll notice we have degrees of freedom again on the left, and along the top it says area to the right of the critical value. So you want to kind of draw a picture here. Again, in the middle, we're expecting the 90%, right? 90%, that's our confidence interval, or that's our confidence level. So there's a total of 10% left, or 0.10. We're going to divide that evenly into the two tails, so 0.05, 0.05. Now again, the table says area to the right of the critical value. So for the chi-squared right value, area to the right would be just this 0.04. For the chi-squared left value, area to the right, well, that would be all the area from this line to the right, so that's 0.95. So now we're going to look in our table. We've got degrees of freedom 29, so we're going to have to go down to 29 down here. And in the table, The left value is going to correspond with the 0.95 column. The right value is going to correspond with the 0.05 column. So we'll go down the 0.95 and the 0.05 column to the row that says 29 degrees of freedom and record those values. So reading from off the table, the left value we get is 17.708. The right value we get is 42.557. Make sure that you keep track of which one's left and which one's right. The right one is the larger of the two. Okay, now based on these two values, we're going to estimate our sigma. Now you'll have to copy down the formula. It's not just plus or minus the error in this case. This is n minus 1 times s squared over, and here's something that can trick people up a bit. The one that is the lower bound is actually chi-squared on the right, even though it's on the left in this sort of inequality here. And then the one over here is going to be our chi-squared on the left. The other thing that tricks people is that when we put in these numbers, 17.708 is going to go in for chi-squared L. There's no need to square this number. This is already squared. So the numbers you look up in the table are already chi-square values, so no need to add an extra square. So here we get n minus 1, which was 29, times our s squared, that was 2.71 squared, divided by the right chi-squared value, which was 42.557, less than our population standard deviation, and then almost the same thing on this side. So be careful you're not squaring those numbers in the denominator. Last step, we can put these into the calculator and see how big these numbers are. In this case, the lower bound comes out to 2.2371, and the upper bound comes out to 3.4680. So our standard deviation is somewhere between 2.23 and 3.47 roughly. And this means that the number of M&Ms in each of these packets vary by, on average, somewhere in between these two numbers, maybe approximately 3 per pack. Now, unfortunately, for standard deviation, there is no program on our calculator. If you read in the book, there is a program you can download, and if you want to put it on your calculator, that's fine. There are also other computer programs that can do this for us. But as far as I'm concerned, we're just going to look at doing this sort of with the formula, and you won't have very many of these questions either. Primarily, your interval estimates will be for proportions or means. Alright, so here's your practice problem here. I gave you 2 problems. One is using a mean and one is for a standard deviation. Again, I encourage you to use the pull-out card that has all the formulas on it as a reference. And for the mean one, I'm going to have you check it with the calculator, but I still want you to go through the process by hand first. That's it for this video. See you next time.